Day 17, we're going to start focusing on elastic collisions. So we're not just looking at conservation of momentum, we're also looking at conservation of energy at the same time. So for this, we're going to talk about billiards balls. So we have a cue ball that is being hit, and it has an initial velocity. Velocity of the cue ball initial is going to be a value of 3.5 meters per second. And we have a mass of the cue ball is 0.17 kilograms. And it is moving initially completely in the x-axis, so we are going to have positive x-axis, positive y-axis, and it is going to collide with the 8-ball. And it is going to go off in some unknown direction, which is what we're trying to figure out. We're trying to figure out the direction it goes in and the velocity. That direction, what it's going to hit is we have a collision here with the 8-ball. And the 8-ball is going to move at an angle of 30 degrees. And it is going to move, sorry, it's not 30 degrees, 35 degrees. Well, that would really throw off the numbers. 35 degrees. And it has initial velocity of the 8-ball after the hit, so we'll call this, 8-ball being an 8 is unfortunate, because we're using a number instead of a letter there. Velocity of the 8-ball is 2.87 meters per second. Meters per second, but you notice that that is not going straight, that is going 35 degrees above the x-axis. Oh, I have these guys labeled opposite. I've got y forwards. I will have to deal with that. I think it makes sense to have our x forwards or y to the right. Sorry, our y upwards are x forwards. So with this, we can assume that the mass of the 8-ball is the same as the mass of our cue ball. So that makes things a little bit easier, and it thematically makes sense. But the first thing we're going to do is we're going to do a big division, and we're going to put everything we're talking about in the y-axis on this side and everything we're talking about in the x-axis on this side. And we're going to just start plugging away. We're going to start with our conservation of momentum equation. So conservation of momentum is going to state that we have our mass of our cue ball times our velocity of our cue ball in the x plus our, at time 1 is going to be the mass, plus the mass of our 8-ball times the velocity of the 8-ball in the x at time 1 is going to be equal to the mass of our cue ball times our velocity of our cue ball in the x at time 2 plus the mass of our 8-ball times the velocity of our 8-ball in the x at time 2. Hoofda. And in the same way, we can say in the y, we have the mass of the cue ball times the velocity of the cue ball in the y at time 1 plus the mass of the 8-ball times the velocity of the 8-ball in the y at time 1 is going to be equal to the mass of our cue ball times the velocity of our cue ball in the y at time 2 plus the mass of our 8-ball times the velocity of our 8-ball in the y at time 2. All I'm doing here is I'm saying sum of my momentums, which is P, or I'm going to write mv at time 1, is going to be equal to the sum of our mass times velocity of everything at time 2. And that is So I have each of my pieces, my mass and my velocity at time 1, each of my pieces, my mass and velocity at time 2. Just conservation of momentum equation here. So everything we're doing exactly the same way as we did our explosions or collisions, except in this case we don't have the pieces sticking together, or we don't have the pieces starting stuck together. We have both pieces on both sides. So this is our two equations, and we will go ahead and start with the y, which is a little bit easier. So our initially our 8-ball is not moving at all, and our cue ball is only moving in the x, so that is 0. So both of those guys come out, and that means that the mass of our cue ball times the velocity of our cue ball in the y is going to be the opposite of the mass of the 8-ball times the velocity of the 8-ball in the y. So I'm just going to start writing those out before I do anything else. I'm going to go ahead and say, I should have done this first. I apologize. Velocity of the 8-ball in the y at time 2 is going to be the velocity of the 8-ball at time 2 times, in this case, it is 35, and the y is going to be sine times the sine of our angle, which is going to be equal to 2.87 meters per second times the sine of 35 degrees, which is something I did not actually plug in. I plugged it all in as one big equation, so give me a second. 2.87 times the sine of 35. I get a value of 1.646 meters per second, and that is positive because we're going up. We said up was positive. And I will go over and I'll do the same thing over here. Velocity of our 8-ball at time 2 in the x is going to be equal to our velocity of our 8-ball at time 2 times, well, if that was sine, this better be cosine of our angle. That is going to be 2.87 meters per second times the cosine of 35 degrees. I assume if I didn't plug in the other one, I didn't plug in this one. Quickly plugging that in. I get 2.35 meters per second, except I probably should have had a negative in front of this. No, nope, that's positive. Sorry, there's a positive there. It is going forward still. Okay, with that done, continuing to work on this guy, going back a step, I can talk about my mass of my cue ball, which is 0.17 kilograms times my, I'm going to subtract that, I'm going to put this on the left side, times my velocity of the cue ball. Oop. Doesn't erase as well with the finger. Velocity of the cue ball in the y at time 2, which I don't know, that's what I'm trying to figure out, is going to be equal to the mass of my 8-ball, 0.17 kilograms, times my velocity of my 8-ball in the y at time 2, which I just said was 1.646 meters per second. Don't need a calculator for this one. 0.17 goes away, 0.17 goes away. I get a value of negative, because I have that, it's the opposite of it. Velocity of the cue ball at y at time 2 is going to be equal to negative 1. I've got 6 fives, but 646 meters per second. There we go. Going to the other side, I'm going to try to get a marker that's going to show up a little bit better. We should keep the same color. Going to the other side. I do have a mass of the cue ball and a velocity of the cue ball in the x at 1. My 8 ball is not moving at time 1. Well, I want to know how far in the x my cue ball is moving at the end. And my mass of my 8 ball and velocity of my 8 ball in the x at 2, I have a velocity of the 8 ball in the x at 2. So starting to plug that in, mass of my cue ball is 0.17 kilograms. You may have already noticed that that's going to cancel out nicely for me, but we're not there yet. The velocity of my cue ball in the x is 3.5 meters per second, is going to be equal to the mass of my cue ball afterwards, which is still 0.17 kilograms. And we're running out of usable marker ink here. 0.17 kilograms, and my velocity of my cue ball in the x at time 2 is what I want to know because I want this overall piece. Probably should say somewhere what I want to find is my velocity of the cue ball at 2 and the angle of the cue ball at 2. So that's up there. And then I'm going to add my mass of my 8 ball, so 0.17 kilograms times the velocity of my 8 ball at time 2 in the in the x. Everything here is in the x, and that is 2.35 meters per second. Okay. Oofda. So first thing I can do is make this whole thing a whole lot shorter. I'm dividing everything by that mass. Nice thing about having these two masses equal is everything's canceling out here. So I have 3.5 meters per second minus 2.35 meters per second is going to be equal to velocity of c in the x at time 2, which is what I'm trying to solve for. And velocity in c of x at time 2, 3.5 minus 2.35 is going to be a value of 1.15, I believe, 1.15 meters per second. It's going to be equal to velocity of the c in the x at time 2. Okay, so those are my x and my y. We'll save our white ink and we'll move to another color. And I want to find my velocity in of the cue ball at time 2, total velocity. So what's happening here is my cue ball is moving, and it is moving in this direction. And I know that the x component of that direction right here is 1.15 meters per second. And I know that my y aspect is 1.646 meters per second. I've got as 1.65 in my notes. That's why this guy's got more decimals than the other, because I don't know the other one. And what I want is I want this guy, and I want this guy. That's my velocity, my angle. So to find my velocity is going to be velocity of the cue ball at time 2 total is going to be equal to square root of the x component plus the y component squared. So 1.15 meters per second, and I'm squaring that, plus 1.646 meters per second, and I'm squaring that. And that gives me a total value of 2.01 meters per second. So this is, do I have space? Yes, I do. 2.01 meters per second. stayed on the board. And then if I want my angle is going to be, let's do tangent. So tangent of my angle, so theta is going to be tangent inverse of opposite 1.646 divided by adjacent 1.15. That is going to give me 55.12 degrees. And there it is, except for one thing. I also want to know, is this perfectly elastic? So everything that I've done here so far, I could have, and it could be non-perfectly elastic. So we could have some loss of energy. We have done nothing here. Everything that we've solved for so far has been conservation of momentum. So if this is a harder problem than I'll ever give you, I don't think I even give any of these on the quizzes, but if I didn't give you guys this piece right here, which I am giving you, I would have, I could say it's perfectly elastic, and that would mean you've got these two equations, and then you have your energy equation, because the definition of a perfectly elastic collision is both conservation of momentum, conservation of energy. So you've got that extra energy equation to determine what's going on. However, that is a mess to figure out. So I am normally going to just give you one of the two values if I'm giving you 2D, meters per second. Okay, writing that guy back up. So, is it perfectly elastic? Well, from how I solved it, I have said that momentum is conserved. And momentum has to be conserved here. So that part is good. Now, is energy conserved? Or is there, like the big sound, the boom from the two billiards balls hitting each other, is that what's going to cause the entire thing? That's energy loss, or there could be heat loss, or there could be all kinds of things where energy is escaping our system. And that could throw things off. So what we need to do here is we need to say, is energy conserved? Our conservation of energy equation is this super long thing. We say that potential energy of 1 plus potential energy of our spring at 1 plus kinetic energy at 1 plus work is going to be equal to potential energy 2 plus potential energy of our spring at 2 plus kinetic energy at 2. Don't talk about height at all. Billiards balls, they're all on the same table. Hopefully that table is level. We don't have any change of potential energy. Springs, definitely no springs going on here. And we don't talk about any work. We're assuming there's no work between the two. So we're assuming kinetic energy at 1 is equal to kinetic energy at 2. And the kinetic energy, we have kinetic energy of the cue ball, and we have kinetic energy of the 8 ball. And there's two different energies there because there's two different moving things in our system. So our equation is going to be 1/2 mass of the cue ball times velocity of the cue ball at 1 squared. That's the kinetic energy of the cue ball. Plus 1/2 times the mass of our 8 ball times the velocity of our 8 ball at 1 squared is going to be equal to 1/2 times the mass of our cue ball at 2. Well, the mass of our cue ball didn't change, so the mass of our cue ball times the velocity of our cue ball at 2 squared plus 1/2 the mass of our 8 ball times the velocity of our 8 ball at 2 squared. All these values, the energy values, it doesn't matter what direction they're going in. So these are the total velocity. So it's this 2.01 not our two values, not our negative 1.65 and our 1.15. It's the total value. We're not going to do a conservation of energy in the x, conservation of energy in the y. Energy is energy. First thing I'm going to do is I'm going to go ahead and cross out the velocity of the 8-ball initially, because the 8-ball starts at rest. Next thing I'm going to do is I'm going to notice that 1/2 is in all of these conveniently, and I'm going to go ahead and cross all of those out. And then the last thing I'm going to do is I'm going to notice that I'd be writing 0.17 1, 2, 3 times here, and they can all cancel as well because my objects have the same mass. So velocity of the cue ball at 1, which is 3.5 meters per second squared, has got to be equal to the velocity of my cue ball at 2, which I just solved as 2.01 meters per second squared, plus the velocity of my 8-ball, which was 2.87 meters per second, and we got that value squared. So if this is true, this side should be equal to that side. And what comes out is I have 3.5 squared, which should be 12.25. And my 2.01 squared, I didn't write down the individual values, 2.01 squared. Again, remember this is me without the full number, so there's probably some rounding errors here. 4.04 and 2.87 squared is going to be 8.24. And in reality, if I didn't round anything at all, 4.04 plus 8, so this is the total of this. That is not what I was trying to draw. Okay. Is 12.28. It's just rounding. I've got this 2.01 has some rounding in it, and that's probably throwing most of it off, and that probably has some rounding in it from when I first created the question as well. So 2.25, 2.28, sorry, 12.25, 12.28, very close to the same number. They should have been the same number. It's just rounding. I'm not going to give you something where it's off by that much, and I'm going to say, oh, it's not perfectly elastic. It's slightly off. If you're seeing it that close, it's rounding. So that is my perfectly elastic piece. I've shown that energy was conserved, and so was the other, because I could have solved this at a bunch of different angles, but only one velocity for that, only that velocity at that angle is going to result in a perfectly elastic collision for this setup. So again, this could have gone away, and I could have solved it with this, and I would have ended up with that number and this number. Way too much work. This is how the 2D problems are going to look, where you're solving for it, and then you're just proving it afterwards. So that is perfectly elastic equation, perfectly elastic condition. So hopefully that's helpful. We got one more to go, a lot faster. So take care.